Yes, we will discuss HCV questions today. So if you have any doubts from HCV, you can send that across to me. Page. So quick recap of the things that we've seen. We learned last time that potential energy and internal conservative force are related like this. That change in potential energy for any system is negative of work done by the internal conservative force, or minus of F internal conservative dot ds. Okay. And from that we saw that the elastic potential energy of a spring is given by the formula half kx square, and the gravitational potential energy of a mass with respect to the surface of the earth, the change in gravitational potential energy is mg delta y, where delta y is the vertical component of displacement. So this is initial to final position for some mass. Then delta y is the vertical component of the displacement. So these are the two formulae in particular that we saw of potential energy. Okay. Okay, so let's start with HC Verma doubts. We will start with question number 10 from HC Verma. Okay, we'll discuss 11th also, Sweta. Okay, so just go through question number 10. I will put it up on the board. Okay, so in question 10, what is happening is we have an arrangement of two blocks kept on a horizontal surface. Okay, so we have a system of two blocks like this. And what we are doing is we are applying some kind of force on the lower block. So this is, let's say, having coefficient of friction mu1, and this is having coefficient of friction mu2. Now what it says is that the force F that we are applying, it produces a common acceleration for the system of F divided by 2 times m plus m. So they're having common acceleration. Okay. So from this, what we can predict is that if you make a combined FBD, of both blocks, you can see that combined mass is m plus m. There's only one horizontal force acting on it. Sorry, there are two horizontal forces, but the other one is friction. this will be mu1 n. So F minus kinetic friction is total mass into acceleration. So substitute this value of acceleration here. Where kinetic friction is mu1 into n. So from equation 1, you will get the coefficient of kinetic friction. Okay, so that's your answer of the first part. Okay, then the second part, we have to find the frictional force acting on the smaller block. So for that, we'll make the free body diagram of the smaller block. So that will be a static friction. So if you look at the upper block's free body diagram, there is only a static friction acting on it. Whereas if you look at the lower block's free body diagram, there is the static friction, there is kinetic friction, and F. So you can see so whether you solve this or this, you can see that the static friction if you solve this, this will come out to be the same. So this is the magnitude of static friction that is acting on the smaller block. And for the last part, we have to just find the work done by friction on the smaller block for a displacement of d. So this block makes a displacement of magnitude t. So during that time, the static friction will be doing a work of so just substitute the value from here. This is the work done. So this is the answer to the third part. So Vashish, hope this is clear. We'll move on to question 11. So many of you are having doubt in question 11. We'll discuss it soon. You'll see that it's related to a question that we've done earlier in friction, especially the second part where we have to find the angle at which we should apply the force so that the magnitude of force is minimum. So Vashish, is this question clear, beta? Okay, finish with this. Then we'll go through question number 11 next. Okay, good. Okay, now question 11, what is happening is that we are applying the force at an angle of theta with respect to the horizontal. So imagine we have a block like this on a rough horizontal surface. And we are applying the force like this. At an angle theta. Okay. Now the details given to us about the block are that the weight of the block is equal to 2000 newtons. And the coefficient of friction is equal to 0.2. Okay. So in the first part, we have to find the work done by a person pulling the box with a chain at an angle theta with the horizontal. It has to be slid through 20 meters very slowly. So it's sliding from here to here through a displacement of 20 meters very slowly. So its acceleration should be tending to zero. So it's moving very slowly. Okay, so first of all, let's understand the free body diagram. So the forces acting on it are this external force, weight, normal reaction, kinetic friction. Such that its acceleration is zero, almost zero, because it's moving very slowly. Okay. So we'll have the relations that normal reaction will become mg minus f sine theta, and f cos theta will be just about equal to kinetic friction. Okay. So substitute this here, and from this you will get this relation. So f's magnitude mu mg on this side. So work done by F. So this is the general expression, and when you substitute the values here, you see this becomes 400 into 20, so that's 8,000 cos theta upon cos theta plus zero point 0.2 sin theta. So this is the expression for the first part, the work done by F in general. Okay. Now for the second part, we have to find the value of theta such that the magnitude of F is minimum. Okay. And then find the work done by F in that case. Okay. So basically this thing, na, find the value of theta so that this is minimum. This all lies here. This expression, in this expression, you have to find F's minima. So remember, we have done this type of question in friction before. Just try to work it out. Yes, what you're saying is correct. Total work done by all the forces will be zero. But then you will have to calculate the work done. So let me explain to others. What Veer is saying that instead of calculating the work done by F, what we can say is that if the acceleration is tending to zero, that means the change in kinetic energy is tending to zero. So net work done should be zero. So that means work done by F plus work done by friction should be zero. But then we'll have to calculate it this way, no? Negative of work done by friction. So that will be minus F into S. So that is minus mu n into S. So that will become minus mu into mg minus F sine theta into S. So that comes out to be the same thing. No? Now when you compare this equation with this equation here, this one, you can see that mu into mg minus F sine theta, that is the same thing as F cos theta. So end up working out the same thing. No? So hope you're following this week, what I'm saying here. Okay. Yes, very good. That's correct, Tej. It doesn't really save time, no? Because it's the same thing, no? इसमें इतना क्या difference है? Because you still have to substitute the value of F, no? See, F is not a given quantity in the question, no? What is given is mg and mu, no? So you still have to find out the value of F here, no? To calculate the work done by F. So that much is still left, no? Okay. If F was given to us in the question, it's a different matter. Then so in this only we can directly substitute, no? Work done by F. Okay, now let's come to the second part. We have to find first of all theta such that F is minimum. So you see the relation between F and theta. F is mu mg upon cos theta plus mu sin theta. So from this you can understand that F is minimum when the denominator, let's think of this like a function of theta, this thing is maximum. Because now from trigonometry, you can see that you can use this trick in trigonometry that we had seen before. That if we have a function like this, you can see that. So the maxima of this function will be square root of 1 plus mu square. So use this trick from trigonometry, then you don't even have to do differentiation. Otherwise, you can also do maxima minima. That method. Okay. So anyway, so F's minimum value will be equal to mu mg upon square root of 1 plus mu square. Okay. And this will be for theta equal to tan inverse mu. So the work done in this case now will become what? The work done by F will become, oh sorry, with this F's minimum value into S into cos theta. Now here theta is equal to tan inverse mu. That means tan theta is equal to mu, which means cos theta will be equal to 1 upon square root 1 plus mu square. Okay. Now in this you put the value of mu as 0.2. And the displacement is 20 meters. Okay, so this is the 11th question. Now next we will pick up 12th question. Finish writing this down first. Okay, so hope this was clear fully. Now let's move on to 12th question. 12th question is fairly easy, so we'll discuss that fast. So we have 37-degree incline, and we have a block of weight 100 newtons. Coefficient of friction on the surface is given to us as, oh sorry, it's a smooth surface. So mu is 0. Okay, now you have to find the work done by a person in moving the block through a distance of 2 meters in two different situations. In the first part, for this displacement of 2 meters, the external force is applied like this along the inclined plane and very slowly. So that means as it is moving, its speed is tending to 0. So a couple of ways you can do this question. One is by simple logic itself, that the forces acting on this are normal reaction, weight, and F, as it is displacing like this. So work done by normal reaction is 0. Okay. Final speed is tending to 0, initial speed is tending to 0. So change in kinetic energy is 0. So work done by F should be equal to change in kinetic energy plus change in potential energy. So work done by this external force is change in gravitational potential energy, because here kinetic energy is tending to 0. So you can see this vertical displacement is h, and that is nothing but s sine theta. So work done by F will be equal to 100 into s, which is 2 into sine 37, which is 3 by 5. So 120 joules. That will be the work done by S. That's one method. The other thing is you can do this, that will be F into S. And since here the acceleration is tending to 0, you can see from the FVD that F balances mg sine theta, and normal reaction balances mg cos theta. So this is the same expression as this. So particularly this work energy approach, the work energy theorem approach, will make the second part much easier to work out. Just make a note of this first. Okay, let's understand the second part. So in the second part of the question, what is happening is instead of applying the force along the inclined plane, the external agent is applying the force horizontally like this. But still the block is going very slowly, so acceleration is tending to zero. So this time as the block makes a displacement of s like this, the work done is, if we calculate it directly, we can see that the work done is going to come in a different way. The displacement s is like this. The force is being applied horizontally. So the work done by F will be Fs cos theta like this. Okay. But to calculate the magnitude of F, we'll have to understand the free body diagram. So because the acceleration is tending to zero, so we have F cos theta will balance mg sin theta, and normal reaction will balance the sum of mg cos theta plus F sin theta. So anyway, so from the first equation, you can see that F is equal to mg tan theta. So from here you can see that work done by F is equal to into S cos theta. So your answer comes out to be the same as the first part. And its logical is that it's the same as the first part because the change in kinetic energy is zero now. That's why I said that it's easier to actually work it out by the statement of work energy theorem rather than calculate this dot product. Okay. Or again, you can see that work done by F is change in gravitational potential because work done by normal reaction is zero and change in kinetic energy is zero. So work done by F is mgh, where h is s sin theta. So it's a one-line statement from this. Whereas here you are having to work out the angle, then work out the force in terms of that angle and all that. Okay. So obviously using the statement of work energy theorem is going to be easier here. So that was question number 12. I hope this is clear. Now next we are moving on to question number 14. Number of people have asked question 14. Okay, good. So question 14 you can do by kinematics also and you can do by work energy also. It is asking that you have to find the average force acting on a car needed to accelerate it from mass of 500 kg and we need to accelerate it from rest to 72 kilometers per hour. through a displacement of 25 meters. So we can see that the average force into displacement is equal to work done by F, and that should be equal to change in kinetic energy. So you can use this. Or you can use kinematics. But this is average acceleration. So this is average force. So we hope this is also clear. Now moving on to next, the 15th question. So in 15, it is said that a particle of mass m is moving on a straight line with a distance varying according to the equation v is equal to a root x. It's a 1D motion along x-axis. So particle is moving in this direction with a speed v. When its x coordinate is x, the speed is given by this relation, where a is a constant. Okay. Find the work done by all the forces through a displacement of 0 to t. So you can see that at x equal to 0, its speed would have been 0 according to this formula. And by the time it reaches somewhere here, x equal to t, its speed is equal to a root t. So work done by all the forces is change in kinetic energy, that is half mv square minus half mu square. This should be work done by all the forces. Okay, so Smriti, hope this is clear. Okay, I'll go back to the 14th one. You can write it down and we'll come back to 15th. Okay, so I think now let's move on to 16th question. Just finished writing down the 15th question if you haven't. And let's move to 16th next. So how we will show that the force does not exceed the value that is given 40 joules in 16th question. So the thing is, see, it is kept on an inclined plane. Now nothing is said whether the inclined plane is rough or smooth. So what will happen is, now when you apply this 20 Newton force, the maximum possible displacement can happen in the situation where the surface is smooth. No, I haven't started the 16th question. Okay, I'm just telling it to you orally. Yeah, this now you can see this. Okay, just a minute, guys. Let me Yeah, so students, as I was saying, for question number 16, the language of the question, if you see, it's like this, that nothing is given about the surface, whether it is rough or not. No? Whereas it's saying that the maximum work done by this force is so much. You have to prove that. So maximum work done kab hoga in 1 second? When in 1 second the displacement is maximum. And the displacement will be maximum in which case? When the coefficient of friction is zero. Understanding? No? So that's the thing. So given the mass of the object, what else is happening? We are applying the force parallel to the inclined plane. Okay. So the displacement, now in this case, it's not a slow movement. You know? So the acceleration is equal to F minus mg sine theta minus kinetic friction upon mass. So the displacement is equal to half at square. So you can see that the displacement's maximum possible value is going to be half F by m minus g sine theta into t square. That is for mu tending to 0. So the work done by F's maximum possible value will be equal to this F into S maximum. So that's how you'll get the first part. That is less than 40 joules, because this maximum possible will be 40 joules. But assuming that the friction is 0. You understanding? We don't know the coefficient of friction. Na? M is given, but mu isn't given. And the time is given as 1 second. Theta is given as 37 degrees. Is it clear? Good thing. Okay. So that's how you'll work out that 40 joules part. Then the second part, find the work done by the force of gravity in 1 second. If the okay, if the work done by the applied force is 40 joules. So in the second part, work done by F is given to you as 40 joules. So that means you assume mu is 0. So that means you know that the displacement will be how much? You know this value because your acceleration will be F by m minus g sine theta. So displacement will be half at square. So now you know that the work done by gravity will be mg dot s or minus mgh or minus mg s sine theta. So you can work it out from this. So can you people finish this question yourself? Yeah, you understood how to do this now. Okay. Okay. Then next we'll move on to. Let's see. Yeah, write it down is fine. This question 1922. Okay. Also have question 18. So B partner, the work done is given to us as 40 joules stage. So we'll assume that coefficient of friction is 0. So once we know coefficient of friction is 0, we know the acceleration. It is F by m minus g sine theta. So we know the displacement. It will be half at square. So then we will calculate the work done by gravity using the dot product. Mg is acting vertically downwards. So it will do negative work. So it will be minus mgh, where h is the vertical component of displacement. Okay, let's move on to question 18. So question 18 is a simple situation. You have a rough horizontal surface on which a block is placed and given some initial velocity. This is the initial velocity. So immediately friction starts acting on it. And we have to find the maximum displacement that the block will make. So mass of the block is given, initial velocity is given, then what else is given? The coefficient of friction is given. So we have to find the maximum displacement that the block will make. So this displacement will be when speed becomes zero. Just use this, that work done by friction will be change in kinetic energy. So work done by friction will be minus mu mg s. That will be equal to minus half mp naught square. So this displacement you can see from here will become v naught square by 2 mu g. Which incidentally you can also use kinematics because you know it has a deceleration of mu g. Okay, Krish, I will scroll up to question 16 also. Okay, that's 18th. Now after that we'll move on to 19th. Actually, in 19th question, Diti, we'll just discuss the concept of power next, and then we'll discuss the question. Power is the rate of work done or rate of consumption of energy. So we'll come back to 19th question. Let's do 20th first. Okay, so in 20th question, what is happening is that a person standing on a ladder, okay, the bucket slips from his hand. Okay, so let's say he's standing on a ladder like this against a wall. Now he has this bucket in his hand, and that bucket falls through a displacement which is given to us, and the bucket's mass is also given to us. The bucket plus the paint in it, that mass is given to us. So what we have to find? We have to find the gravitational potential energy lost together with the paint. So change in gravitational potential energy is mg delta y now. So you can see here delta y is minus of s, whatever vertical displacement he's had. So it is minus mgs. That is the loss in gravitational potential energy. Is it clear, Diti? So just put the mass of the bucket and the paint that is given. This is 6 kg, S as 2 meters, and G as 9.8, and you will get the answer. Is the concept clear, beta? Take G as 9.8. Okay, now let's move on to question 22. Okay, so 200-meter freestyle swimming race. Okay, Olympic record was when in 1 minute and 57.56 seconds it was covered. Okay, this also has to do with power. So let's just discuss the concept of power, then we'll come back to these questions. We haven't discussed the definition of power now. We'll come back to these questions with the definition of power. Okay, so we'll discuss the remaining questions also, but first I want to discuss the concept of work energy theorem that we were seeing last time, and then the concept of power itself. So work energy theorem statement is like this, that work done by external forces plus work done by non-conservative forces is equal to change in kinetic energy plus change in change in potential energy. This is the general definition of work energy theorem for any system. Okay. Whereas earlier you have seen the definition of work kinetic energy theorem. That was that net work done is equal to change in kinetic energy. So you can see that there's a correlation between these two, because you can split the net work done into work done by external forces plus work done by internal conservative forces plus work done by non-conservative forces. That's equal to change in kinetic energy. So if you compare this with this, now you can see that change in potential energy is nothing but negative of work done by internal conservative forces. So that is just the definition of change in potential energy. Okay, so that is the correlation between the work energy theorem defined for a system with respect to the work kinetic energy theorem that is defined for a single body. So let us see this in application. So for example, let's take a situation where we have some conservative force as well as some non-conservative force as well as some external force. So take this system as an example. Okay. So spring constant is given to us as, let's say, 50 newtons per centimeter. The mass of the block is given to us as 2 kilograms, and the coefficient of friction is 0.2, let's say. Okay. Now, initially, the system is at rest with the spring relaxed. See, the block is at rest, not necessarily the system. The block is at rest with the spring relaxed. Okay. Now, at time t equal to 0, a constant horizontal force of magnitude 10 newtons starts acting on the block. So we start applying a force like this on the block. So you want to find the speed of the block when its displacement is 0.2 centimeters or 2 millimeters. No, so by the time the displacement is 2 millimeters, you have to find how much speed the block will have. Okay. So just note down the question, the data of the question. Then we'll understand this question by two approaches: work energy theorem applied to the system versus work kinetic energy theorem just applied to the block alone. Okay, so let us see how we can apply the approach of either thing. Okay. So as the block is moving, let's say after some time it has reached a state where the spring is extended by L plus X and the block has developed a speed V because of the application of this external force F. Going from the initial state where the speed of the block was zero and this was at natural length. So the block has made a displacement of X. So while making this displacement, what is happening is on the block there is spring force, there is kinetic friction, and there is external force. And there's all this. Okay, so if we go by, so if we apply work energy or if we apply work kinetic energy theorem to the block, we have net work done is equal to change in its kinetic energy. So net work done will be the work done by the external force plus the work done by the spring force plus the work done by friction, and there should be change in kinetic energy. Now F is a constant force, so work done by F will be Fx. Okay. Work done by spring force we'll have to calculate by integration of, so that is minus kx dx integrated from x equal to 0 to x equal to x, and work done by kinetic friction from this. So we'll have this Fx minus half kx square minus mu mgx is equal to half mv square because the initial speed was 0. So this is how we'll get the value of v. So from this we'll have to calculate the value of v. After substituting everything that is there, okay, all these things. Okay, so substituting all this, we'll get the value of speed. Yeah, force is 20 newtons. Actually, it's not 20, it's 10 newtons. Yeah, correct. I'll make the correction. So the force correctly should be 10 newtons. minus half kx square minus mu mg x. This should be half mv square. So this is a relation. Okay, so okay, final answer and all is fine, but it is more about the application. Okay, now next we'll see that we can, instead of applying work kinetic energy theorem, we can also apply work energy theorem to this thing as a system. Now that is the more important thing that we're interested in. So what we can do next here is take our system as the block plus the spring, and then apply work energy theorem. Okay. So when we take this as our system, what happens is that spring force becomes an internal conservative force. Okay. F is the external force, and kinetic friction becomes the non-conservative force. Okay. So while this block is moving, we'll say is equal to change in kinetic energy plus change in potential energy. So in general here it will become work done by F plus work done by kinetic friction is change in kinetic energy plus change in spring's potential energy. So as you can see, going from here to here, the work done by F will be plus Fx, but the work done by friction will be minus mu mgx. The change in kinetic energy will be plus half mv square, so it's going from 0 to v. And change in potential energy of the spring will be plus half kx square. Okay, because this is what we are taking as the initial picture, is what we are taking as the final picture. So in the final picture, you can see the potential energy of the spring is half kx square, and the kinetic energy of the block is half mv square. Whereas in the initial picture, you can see the potential energy of the spring was zero because x was zero, and the kinetic energy of the block was zero because the initial speed is zero. Okay. So this is the initial values. These are the final values. So accordingly, we have written this term and this term. Okay. Now, if you just compare this term with what we have got from the work kinetic energy theorem earlier, you'll see it's exactly the same. Okay, so you compare this with the earlier equation and you can see that it's exactly the same. So this reduces to the same thing, that half mv square is equal to fx minus mu mg x. minus half kx square. So you get the same thing. This is exactly the same equation as what we've written earlier. So this is an example where we are looking at the comparison of work energy theorem with work kinetic energy theorem, and you see that the two are exactly the same when you substitute the values properly. But the advantage of using work energy theorem is instead of calculating work done by spring, we're directly substituting the formula for the work done by spring. It makes it that much easier. Okay, so hope this is clear to all of you. If there's any doubt, just let me know. You want to write down the earlier part? Stage. Okay, done. Okay. So what I was saying is, if you saw the earlier part, this equation, this one is the same as the final equation that we are getting here. These two equations are one and the same. Okay. Now next thing we'll see that in a situation where if work done by external force is equal to 0 and the work done by non-conservative force is also equal to 0, then for a given system, okay, then its mechanical energy, mechanical energy of a system is defined as the sum of kinetic energy plus potential energy is conserved. Okay. So basically you can see that for these two terms to be 0, change in kinetic energy plus change in potential energy is 0. Okay, so that means the sum of kinetic energy plus potential energy is constant. That's why the change in the sum is 0. So this is basically, this situation is called conservation of mechanical energy. Okay. So we'll see a lot of situations in which this happens. The simplest situation of this is, for example, if you have projectile motion. You project something at a speed u at an angle theta, and as it goes like this, you know, at the highest point, the speed becomes u cos theta. Okay, so let's say this is the point B, this is the point A. So if we take the Earth plus the particle as a system, so we can see that from A to B, there is no work done by external force, there is no work done by any non-conservative force. There's only gravity doing work, which is the internal conservative force. Okay. So we can say that for this system, change in kinetic energy plus change in gravitational potential energy is 0. So A to B, you can see the change in kinetic energy is plus half mv square minus u square. Change in potential energy is minus mgh. So that is 0. So it's plus mgh, which is 0. So you can see that we get h is equal to u square minus v square by 2g. So the maximum height in projectile motion, which you know from kinematics as a formula like this. You can also see the proof of this from work energy theory. Okay, so this is just a simple example of conservation of mechanical energy. In any projectile motion, whether it is oblique projection like this, or vertical projection, or horizontal projection from a height, whatever be the case, mechanical energy conservation can be applied so long as there is no wind resistance or no air resistance. So just make a note of this example and this concept of conservation of energy. This will also be applicable in number of questions in future. And then we'll also discuss about power and those two questions 19 and 22 from that. Yeah, I'll scroll down. Karan. Did you finish with that question on top, the work energy theorem question? Okay. Okay, so hope this is clear. So as I said, we'll see conservation of mechanical energy in number of situations in future. Now, next, you just think of conservation of mechanical energy as a special case of work energy theorem. When the work done becomes zero, work done by external plus non-conservative, that thing becomes zero. Then the change in mechanical energy is zero. So now let's discuss the last part of the theory here, which is power, the concept of power. So power P delivered by a force acting on a body or particle or whatever. So this is defined as, this is actually, when we say power P delivered by a force, what we mean by this is instantaneous power. It means power at a particular instant. Okay, so that power, it is defined as instantaneous rate of work done by that force with respect to time. Okay, so power is defined as this. Okay. Now we know that work done by a force is integration F dot ds. So work done in a differential time dt is F dot ds. Okay, so therefore this can be written as F dot v, because the instantaneous rate of displacement with respect to time is nothing but the instantaneous velocity. So while the definition of instantaneous power is this, that it is the instantaneous rate of work done with respect to time, but as a formula, it also comes out to be the scalar product of force and velocity. Okay. So rate of work done with respect to time is actually equal to scalar product or dot product of Fn. So if a force F is acting like this on a body which is having instantaneous velocity like this, where this angle is theta, it's like this. So this is the first definition in context of power. Instantaneous power delivered by a force F is defined as instantaneous rate of work done with respect to time. Okay, now next definition we'll see is average power. Okay, all right. So the second part is the definition of average power. Oh, but before that, let's also write down about the unit of power. Then we'll come back to this. So dimension of power is dimension of force into velocity or dimension of work done upon time. So you'll see that becomes so t to the power minus. So SI unit of power is watt. So 1 watt is equal to 1 Newton meter per second, or it's the same thing as 1 joule per second. And CGS unit is erg per second. Okay. But SI unit is the more important one. Now there is also an alternate unit of power that is used sometimes in mechanical engineering, and that is horsepower or British horsepower. Both the names refer to the same unit. Now, 1 horsepower of British horsepower is approximately equal to 746 watts. Okay. Now let's come to the definition of average power. So as the name suggests, average power is average rate of work done with respect to time. So the average power delivered by a force in time delta t is the total work done divided by the time. Okay. And the third thing that we have is that since net work done is equal to change in kinetic energy on a body or particle, okay, so therefore rate of net work done with respect to time becomes rate of change of kinetic energy. So that is net power. So net power delivered on a body or particle equals to the instantaneous rate of change of its kinetic energy. So these are the three aspects of power that we should understand. So for example, question number 19 that we were talking about earlier. Let's quickly discuss that. Okay. So HCV question number 19. So what is happening is there is water is falling from a height of 50 meters. Okay. And we are using that. So from a height of 50 meters. So we have a continuous stream of water which is falling. The water is falling at the rate of 1.8 into 10 raised power 5 kgs per hour. Okay. So what we can understand is that if mass delta m of water falls through a height of h, okay, then the loss in gravitational potential energy is minus delta m gh. Okay. So if this energy is now being converted into electrical energy, okay, now it says that 50% of gravitational potential energy is converted to electrical energy, okay, through a turbine. Okay. That is the concept of hydroelectricity. So here the efficiency of that process is 50%. So there will be some dissipation of energy, but 50% will be converted to useful electrical energy. This point is clear, Diti? That when delta m mass is falling through a height h, okay, the electrical energy that we will get is 50% or 0.5 times delta mgh. Hope this point is clear. So now the electrical power that we will get, electrical power output, that is rate at which electrical energy is being generated. That will be 0.5 times this. Okay. So as you can see, this is in joules. So now this is in joules per second. So you just have to substitute this value. This value that we've got now, this is only our delta m by delta t. It is 1.5 into 10 raised power 5 kg per hour. So that is the same thing as kg per second. So now substitute that over here. The electrical power generated is 0.5 into 1.5, 1.8 into 10 raised power 5 divided by 3600 into 9.8 into whatever height was given to us as 50 meters. So this power that we'll be getting is in joules per second or watts. Okay. So now this divide this by 100 watts and you will get the number of bulbs that are illuminated by using this electrical power generation system. So hope this is clear. Okay, so this was question number 19, especially you have asked Titi, so hope this is clear to you. So if each bulb is 100 watts, then just divide the total power by the number of bulbs, and that will, okay. So similar way you attempt question number 22 also, we'll discuss that in the next lecture. Yeah, sure, I'll scroll up. So just take this down and that's it for today's session, people. Yes, we will discuss the remaining doubts of H.C. Verma in the next lecture. So now try and finish up H.C. Verma at least up to question number 50. Because after 50, there is the vertical circular motion questions, which I'm sure you've done in circular motion chapter. So try to finish up to question number 5050 from H.C. Verma. We'll discuss them in the next lecture. Okay. Yeah, so that's it for today, people. Wish you all the best. Bye. Yeah, I will send the notes. Yeah, I'll send